Okay.
Welcome everyone. I think we can get started. I'm pleased to introduce Steinweg. Steinweg is a senior data scientist at Honey. He currently works on the personalization team focused on product recommendations and discovery. He will be presenting a talk titled E-commerce Product Categorization at Scale. Please join me in welcoming Jesse.
Thank you very much. I'm very excited to give this talk today. Thank you all for being here this afternoon. So I work at a company called Honey. I don't know how many, show of hands, how many of you have heard of us before? Oh my goodness, that is great. I love seeing that. Okay, I'm going to tell the marketing team. So I guess all of you pretty much know what we are, although we have some other projects we've been working on that aren't as obvious to everyone. So I'll explain it for everyone that's not necessarily familiar. What is Honey? The main thing we're known for that most of you are probably familiar with is the browser extension. So the way the browser extension works, you install it in whatever browser you want, Chrome, Safari, Opera, etc. And when that browser extension is installed, whenever you go around and shop, you no longer are going to have to search for coupons again. So basically, when you go and do your normal shopping behavior, you're about ready to check out, and you're like, I wonder if there's a coupon out there that will save me 10% on this. Don't worry, we've got you covered. All you have to do is this nice little pop-up will show up, and you just click the Apply Coupons button, and voila, we will scan the entire internet, find all the coupons, and apply it automatically for you on checkout. So you don't have to do anything. And this actually works pretty well. My wife and I have already saved over $100 this year doing this. It's pretty easy. There's not much to do. And it saves a lot of work of trying to find coupons. So this is great. We also have rewards with some of our special vendor partners. So sometimes you'll get a 1 to 5% Honey Gold cash back that you can eventually redeem for a gift card in other cases if there's not a coupon available. The other thing that we've been working on that we're very excited about is a new shopping app. So I don't know how many of you have been in a situation where maybe you go on Amazon and it doesn't quite have what you want, it's not in stock. I know I've had this problem with Star Wars Blu-rays. Amazon doesn't play nicely with Star Wars Blu-rays. They aren't available when they come out, so I have to go find them somewhere else, usually Best Buy. But wouldn't it be great if you just had to go to one place to do all of your other shopping? So let's say you wanted to buy something from Best Buy, something from Walmart, something from Target, something from Macy's, doesn't matter. You wouldn't have to have a different login and password and address you want things shipped to, credit card information. You wouldn't have to do any of that anymore. You just go to the Honey Shopping app and all of it will be available to you at your fingertips. Pretty cool, right? So, given that's what we're trying to do is make the shopping experience better for people, one problem we run into is now we have a bunch of different catalogs from a bunch of different stores. But we aren't the store. We're kind of a storefront. So we had no control over how that product catalog was created. So if you want to have a good shopping experience across hundreds or even thousands of stores, what you need to do is organize the products in some way you can find them. So imagine, let's take a grocery store, okay? Now, imagine what would happen is if you went to the grocery store and there were no signs on the aisles on where all the products were you needed to buy. And even worse than that, the products weren't even organized in any fashion. Now, how long do you think it would take you to get your shopping done? Quite a long time. So that's the idea behind this is we want to group all of the virtual online store, given this is hundreds and thousands of stores, into different categories. So you can find what you want. So for example, if you want to find table lamps, we'll have all the table lamps from all of the major vendors. Otherwise, it may be very difficult to find the table lamps that you're looking for. So what we have to do is take hundreds of stores and kind of squeeze it down into one unified product categorization taxonomy, right? But they all sell different things, they all specialize in different goods, and they all have slightly different ways of labeling things. Some stores don't even label things at all in categories. They just want us to figure it out somehow because they think it's too much work. So how are we going to approach this problem? Let's say, for example, that we have these two items. One is a wonderful AT&T 4-line cordless desk set, I'm sure very popular these days. But let's say you wanted to buy one for whatever reason. An example categorization for this product would be, these categories are hierarchical. So office products would be the very top of what we call the breadcrumb, And then each layer down is hierarchical and parses the products with more precision. So it's an office electronic good, under telephones and accessories, landline phones, okay? So that's how product categorization would work. This product, a Click and Grow Smart Herb Garden 3 Starter Kit, well, what in the world is this thing? Because it's kind of like a gardening thing, so maybe it goes under gardening, but it's not grown outdoors. Maybe it's home decor, but it's not really because it's a plant and it's not a typical home decor item. So how do we categorize this? That's very difficult. So you can imagine trying to ask machine learning to figure this out is even more difficult if humans can't even agree on where this belongs. This can be a very challenging issue. So how are we deciding to try to tackle this? The current solution we use is something we call manual mappings. So just think of a simple key value store. So if a vendor labels a certain category that they've chosen all their goods to be under, let's say Macy's, for men/underwear and socks. We have someone sit down, look at the products that Macy's has in that category and say, okay, based on my human judgment, I think this belongs under the category we have of clothing, shoes, and jewelry /men/clothing/underwear. Not bad, right? But the problem is they grouped underwear and socks together. Some vendors do that, some don't. So the problem is, unfortunately, some of the socks are going to end up in this category. So it's not perfect. But the beautiful thing about this is you can do it pretty fast because each category contains potentially hundreds or thousands of items and then you're done. And you can trust that the label that the item is given is probably going to be accurate. And currently we have about 27,000 of these manual mappings that have been done by hand painstakingly by a couple of our workers at Honey. And we map them to a fixed product taxonomy. For now it's fixed. We'll probably make it more flexible in the future to around 3,000 different categories. It's quite a lot, right? So there's some pros and cons to this technique. One great thing about it is it scales really well, given that the mapping covers several items at the same time. So if you need a solution really fast, this is great. It's very easy to implement because it's just a simple key value lookup. You can just do a merge on a table and you're done. It allows pretty decent coverage of products. Currently using this method, about 56% of our products have a category assigned. So product discovery is actually pretty good for the most popular items, but we do have some issues in the long tail. The cons of this is if the merchant doesn't have a category assigned to the product, or if we can't figure out what the category that item was assigned to based on the parsing that we get, we can't use this method. So there's just no way to label it. So there are some stores where we have no items we can categorize at all, which is not good. It is a very manual, time-consuming process because a human has to do it one at a time for every single category that a merchant has. And some merchants have thousands, so it can take a while. And the other problem, as I pointed out, is the emerging categories sometimes cover a very broad range of products. Like some of them will just say men's things. Not very helpful, sorry. So in those cases, we have to be very conservative in what we label it as. So we just say it's, well, if it's a clothing shopping site, we'll say men's things is just clothing, shoes, and jewelry, which is the very first level of precision in the breadcrumb. That's the best we can do. But this also causes a problem in the training data, right? Because there might be items you want to label more precisely than that, but that's the best label we can come up with in this kind of human-assisted fashion. So the solution that we've proposed is a human-machine hybrid. Now, I know Professor Xavier's technically not a human. He'd get mad at me for saying that, but forgive me. The idea is you take the best aspects of human and their domain knowledge, kind of like a Bayesian prior, right? And then you mix that with the automation process of machine learning and try to marry the two together in a nice coupled solution. And here's a flow diagram of roughly how this would go. If any of you are familiar with this space, you may be familiar with a paper that Walmart came out with in 2014, where they did something very similar to this. So I'm going to just walk through this diagram as kind of a high-level overview of how this would be done, and I'll go into the details of each of these little steps later. So let's say you have a bunch of products that come in. You have no idea what category they belong to. You then have to figure out, let's take 3 different techniques to categorize these products. So one way you can do that is something called regex rules, where you simply have regular expression matching of terms in the title. The other is the model ensemble, which is the cool, fun part that I'm sure most of you are here for. And then there's the store rules. So for example, if you have a store that almost never sells jewelry, then you know if any of the models predict jewelry, that's just wrong, and you can cancel it out. Then you have the voting master who takes in all these predictions and information and kind of combines them together in an ensemble vote, majority vote, and tries to see if there's any agreement between all these different methods. If there is, great, we can classify the item. Hooray. Now, in addition, we also have a separate holdout set that we can check to see what the model performance is over time. So if the stores that are coming in are very new, we don't have a lot of training data on those stores, we can say, uh-oh, the performance of the models in the holdout set is really bad. Something must have gone wrong. So we can go back and figure it out and fix it. The voting master decides whether the items should be classified or unclassified. If they're classified, great. But to check to make sure in an automated fashion that this is actually working, we can use crowdsourcing. So for crowdsourcing, what we're doing is we say, here's the product, here's the title. Can you tell me if you think this categorization is correct or not? And we do a statistically significant sample. I'll go into more details about that. And then if the crowdsource workers say, nope, those aren't good, you got to fix it, we take the rejected samples and go back to write some additional regex rules to cover the edge cases. And we take the final labels that were classified, and as long as the crowdsource workers say your rate was OK, then we get the green thumbs up, we add them to the catalog. So that's the basic idea behind this whole process. And I'll go into the details now. The model ensemble. So basically what we're doing right now, we're trying to keep it fairly simple. We just use text features and image features, that's it. So for the text part, we take the item's titles. For example, this is an Acme Katana Chrome table lamp. And the merchant category, if available, sometimes it's not, that was assigned to the item. So in this case, it was assigned to essentially table lamps. And then we feed that into the text-based model. A separate model is trained just on the image of the item. So we take the image of the item and stick it into the image-based model. And this is what the architectures look like. So for the text-based model, I know this is a little complicated. If you want to get a better overview of the text model architecture, it ended up working the best. It's actually from another Walmart paper. It came out in 2018. But essentially what we're doing here is we kind of have two heads. It's almost like a Siamese network in a way, where you have the titles that come in here, and then you have the merchant categories that come in here. And for the titles, we have a maximum vocabulary of 75,000 most common tokens. And then for the merchant categories, the 7,500 most common tokens, because the vocabulary for merchant categories is a lot less diverse. Once you get the embeddings into 100-dimensional vectors, you then apply convolutional neural networks to those on varying strides of 2, 3, and 4. So kind of think of these like bigrams, trigrams, and 4grams. And then you do max pooling on those, each separately. And then you use dropout, because you can have some overfitting issues since the 2-gram and the 3-gram are probably going to be very similar. You do the same thing for the merchant category. And then you finally combine the two together at the very end, do one last dense layer with a ReLU activation function, and then finally apply the softmax at the very end, all of the categories. Now for the image, we haven't quite gotten to this yet, but this is the design process I like. It also comes from the same paper, although I was going to use a different model base for the transfer learning. In this case, I like exception. It got very good performance on ImageNet. So what we do is we take the very top layer of that pre-trained model off, and then we stick on these new layers. So in this case, we take the model as is, frozen. We don't want to update any of the weights. Maybe later we'll peel off some of those weights and retrain them ourselves. But for now, we'll leave it alone because it speeds up training quite a bit. And then we will have very thick, dense layers after we feed in the image of the output from the transfer model of 4,096 dimensions with 2 ReLU activation functions for each of the layers. And then the final softmax, same as before. Now, this is the part that I think is the coolest. I've been doing data science now for about 3 years, and one thing that's been a pain point for me, I don't know if it's been a pain point for many of you, is this entire process of getting the data, formatting the data, creating the features, training the model, especially if you have to do it at really large scale, or training it on a GPU. To do that in an entirely automated process is difficult. Well, I can safely say now it's actually possible to do. So how do we do this? We take a couple of key pieces. One is Airflow. If any of you are familiar with Airflow, it's great for automatically scheduling jobs. Usually it's used for ETL jobs and data engineering. But you can do other things with it, like automatically train and score models, which is nice. And we also use a lot of Google Cloud products at Honey. They're a big partner of ours. And we use something called Google's AI Platform. It's very similar to Amazon's SageMaker, if you're familiar with this. So what it essentially allows you to do is train a model on a specific virtual instance that's available automatically and has all of the CUDA NN libraries pre-installed. And then you can get a GPU instance of any size you want, run the model on that, train it, and when it's done, you can continue with the rest of the pipeline. This is really great because you can now train at scale, and you can train very quickly. And it's not such a headache anymore to have to automate this entire process. So Airflow has a bunch of operators, if you're not familiar with it, that kind of couple from one step to another. It's a direct acyclic graph. And once one step is finished, it proceeds to another step, and then to another step, etc., so that the next step doesn't continue until the prior step is totally finished. And then you just kind of connect the steps in order like this. And this takes care of the entire pipeline from getting the training data to training the model to uploading it so that it can be scored later. And the model we train on TensorFlow, of course, because that works very well with Google's products, on the AI platform. And so it's essentially a model package that you create with TensorFlow code. It's a Python package. The Python package then gets installed on the virtual machine. So this is essentially what the Airflow diagram looks like. I'll walk through it very briefly. These are the steps involved in getting the train and evaluation set splits. After that, we do all of the feature engineering and pre-processing, which is eventually a bunch of BigQuery and Google Cloud Storage operators, just copying data in and out, that sort of thing. That's all it is, really. And then you create files. You can also have Python operators that run very small snippets of code, but be careful that you don't have a Python operator operate on very large amounts of data. It needs to be for very tiny procedures. If you need scalable stuff, you should leave that to either BigQuery or to Dataflow, which is based on Apache Beam. It's kind of like Spark. And then what you do is you create the model package. This is TensorFlow code. It takes all of these pieces that it needs in order to package the model. And then this is the cool part. It will train the model on a GPU or even a TPU if we wanted of our choosing. So you can configure that as a parameter when you start the job. And then once the model is trained, this will send a message to the next step in the pipeline saying the model is done. I'm going to find the model path where the TensorFlow file was saved for the latest checkpoint. And then I'm going to upload the model to Google's AI platform system. What that gives you is the ability to have an API now that you can score the model from. So you can either do batch jobs through it, where Google will smartly parallelize the code, copy the model, and then do batch scoring. Or you can even have a live API endpoint that you can hit. So you can send JSON requests to and forth from the model endpoint, which is really nice. Now, regarding the store rules, these are some quick examples. Home Depot is not going to be selling jewelry probably anytime soon. I doubt that's in their business model. So if we predict jewelry from Home Depot, that's a no. We can eliminate it. Same thing for ASOS, which is a fashion online retailer. They're not going to be selling electronics. Newegg is a computer parts store. I've built a couple computers from them myself. I believe they're now on our app, so you can shop Newegg on our app if you'd like. And there are no shirts or dresses from Newegg. So this gives you a rough idea as a check we can do. Now for the regex rules, these are pretty simple to understand, but they're very complicated to create because you need to have very high precision but very low recall so that the rules don't kind of overwrite each other. Some examples would be if the word greenhouse is anywhere in the title, then we are going to assume that it falls under greenhouses and accessories for patio, lawn, and garden. A duvet, which is kind of a fancy name for a sheet cover on a bed. So if it ever says duvet, which is kind of a weird term, we're always going to categorize it to duvet covers. And then iPhone case, of course, we want that to be a cell phone accessory. Now, the voting master, this is how it works. So what you do is you combine the votes of the image and the text model along with the regex and store rules. Now, these categories, we can prune them to less precise levels because we have too much uncertainty about the model predictions. Say they disagree too much. That could still give us an accurate category assignment, maybe not as precise as we'd like, but over time, as we get more and more data coming into the system, we now have over 20 million training examples that I could train on, and that grows about 2 or 3 million a month. Eventually, the models will get smarter and smarter at this, and they'll get more and more precise. But our goal really is to provide a category that's just not wrong. We don't want to see women's dresses inside of automotive parts, okay? That's embarrassing. We don't want that. So that's the goal here. So let's pretend in this example that the text model predicted this was a women's boot, but the image model said, no, that's a men's boot under work and safety. But the regex rule said that's a men's boot of type Chelsea. Well, none of the models quite agree, but they do agree on some things. As long as 2 out of the 3 agree, that's a majority vote, and that's OK. So if we look at each of these breadcrumb levels, they all agree on clothing, shoes, and jewelry. 2 out of 3 agree it's a men's item. All 3 agree it's a shoe, and all 3 agree it's a boot. So this is the final vote because there was enough agreement, and therefore that's how we can categorize it. Make sense? Now, this is the performance we have on a holdout set of 77,000 items across 3,100 categories to give you an idea of the scale. So if you're flipping a coin and predicting a category, your odds of getting it right just through random chance would be 1 in 3,100. It's pretty small. These are the precision levels for each breadcrumb depth. So the highest being the most broad breadcrumb and the lowest breadcrumb level being the most precise breadcrumb. And the precision are these scores here, which we're actually pretty happy with. If you think about how difficult it would be to predict these across 3,100 categories. Getting precisions in the 90s or 80s is really good. Unfortunately, on an e-commerce site, we need to be just a bit better than this. So we're not quite happy with this yet. We're close. And the overall recall, by the way, is about 50%. So the other 50% of the time, the models just don't agree enough to offer us a prediction. So what do we do in order to make sure that these model predictions are being validated? We're not having a human check it every time at work because that would take too long. So we use crowdsourcing to do it. So an example of something we can do is take one of the predictions that are outputted by the ensemble. We take a statistically representative sample. So it's similar to polling in national elections. If you want to figure out which candidate's winning in a race, you don't necessarily need to poll every single person in the United States. You can just poll a statistically significant sample that actually ends up usually doing a good job. So that's the idea here. We just take a random sample of these as statistically significant and then check to see if the categorizations are right. So we ask our crowdsourced workers, we'll say, here's a product we categorized, do you agree with this? So we give them the title of the product. This is a hairdryer. Here's a picture of what the hairdryer looks like. And then we ask them this question. Is the following categorization correct based on what the model ensemble agreed on? And they just vote yes or no. So making it a binary question is really important for crowdsourcing. You want to make it a very simple task that people can complete in a very short period of time very quickly. That makes it cheap and that makes it scalable. So this is a way we can kind of correct automatically without having people at work having to do it. So these are some conclusions of the work. Walmart's public success utilizing this framework was overall, in the end, they got 93% precision and recall for categorization of their products. We're in a bit of a different boat, though, because we don't just have to categorize Walmart's products. We basically have to categorize everybody's, except Amazon, of course, although we do have a lot of Amazon data. The automation process is key because we want these models to stay fresh. We don't want any drift. So we can automatically schedule a new model to be trained every day or every week or every month, whatever time we want. This process will be fully automated, so we don't have to worry about it anymore. So the models are never going to get stale. They'll always be fresh. And that's really hard to do, as I said previously, if you have to train on a GPU. That's kind of hard. But this process is now fully automated thanks to Airflow and through Google's AI platform. That's great. And the third is you can combine human domain knowledge and machine learning to take care of the automation part, and that can lead to very strong results. So that's essentially how we're trying to tackle this problem. And that's my talk. I'll leave the rest for questions.
So cool to see how you've laid out this model. Like, it's just fantastic. And I'm very happy about the automation, too. I share your enthusiasm. Can you talk a little bit? So I have two questions. The first is, can you talk a little bit about the regex component? Because it seems like that would be like a very heavily involved process. Do you know what I mean?
Yeah. I was very skeptical of even trying it at first. I read it in Walmart's 2014 paper. They were adamant this is the only way that they could handle all of the edge cases they were dealing with. And Walmart went a step further. They said, we're not even going to trust the merchant categories that are assigned by merchants. We're going to do them all ourselves. So the only way they had to solve this problem was to write some basic regex rules to start with. And Walmart's already written tens of thousands of these, which took several months. And I've just started doing this. I only wrote about 750 rules myself. It was a very time-staking process. And what I've concluded is, I think the regex rules would help for the edge cases where the models just aren't able to do it because our data is very noisy. It can provide greater precision and a greater check with the ensembling process. But the downside of that, it's very brittle, it's very hard to maintain, it takes a very long time to write these rules. So if I had a year to say write these rules over time and we had tens of thousands of them, I think we'd be in much better shape today than we are right now, but that's going to take time. So unfortunately at my company what we've decided to do is put this on hold for the moment, partially because we didn't get to train the image model the way I would have liked. dumping 14 million images through a system and then setting up what are called TF records in order to do the training process is extremely data intensive work. It would have maxed out our data flow quotas. And so we would have had to kind of fight with engineering about what those are, and we would have had to make some changes. So for the moment, we're putting this on pause, but we're going to resume this work again next year. I am curious to see if we got somebody writing regex rules on a regular basis that were correcting the issues that the models just kept getting wrong, if we could get the performance results we wanted. Walmart said this is the only way they could get this done.
The crowdsourcing piece, are those your members, or are you like sending this out to like a third party?
No, we send this out to a third party for crowdsourcing. So there are several examples available. Amazon Mechanical Turk is probably the most commonly known one, where you just send a bunch of tasks up and then have crowdsource workers bid on whether they want to do it. Then they do it, and you get the results back. You can also use other third-party services like Scale.ai or Crowdflower, that kind of thing, where they have their own workers on staff. You just send them the questions through sometimes like an API or something. They'll answer them, and they'll send the results back to you.
Thank you.
Yep.
So follow-up question on that. How do you close the loop? So once you get the feedback from crowdsourcing agencies, how do you get a tag somewhere that, okay, these models are working better than the other ones? Like, how do you close that loop?
So what we would do if we executed this, which we probably will next year, is take the crowdsourced sample. We check to see what percentage of them the crowdsourced workers think we got correct. And as long as that's above a quality control threshold, we say, OK, this batch was classified correctly. We can add it to the catalog. If it's too low, then we have to go back and see what went wrong. So it could be there was a model issue where the model was too old. There was a new store that came in that had a lot of products we've never seen before. There could be issues with maybe some of the regex rules are overlapping with each other too much. We would have to go back and figure that out. But what Walmart ended up doing is they just wrote a bunch of regex rules to fix all the mistakes. And then they would run everything back through the pipeline again and then see if that fixed the problem. So that's kind of how the feedback portion works.
I'm just a little curious as in determining the product categorization, you use text-based model, image-based model, and also REST rows. So I just wonder, are these models accuracy or the importance in determining the product category is the same? If they are not the same, maybe we could put different weights in different model instead of just use majority vote to get your product.
Yeah, we considered that. I haven't ruled that out. It is a possibility. One thing we thought of doing is looking at the confidence of the scores. So all of the neural networks produce probability scores for all the classes, and then see how confident they were, and then pick the most confident one, or think of some way of voting the probabilities by a weight. The problem, though, is that I noticed the text model kept going to the extremes, because with text-based models, if there's one or two keywords in there that are very often associated with just a single category, then the model confidence is off the charts almost 1. And in that case, it's very, very difficult to weight the different probability scores in a way that works. So I decided to come up with this kind of majority voting scheme, and that seemed to be working the best in the testing that I was doing.
So there are newer models and systems like Google BERT and Excelnet and I think Google AutoML. Have you tried experimenting with those, or do you think those would be overkill?
So AutoML, yes, I should have mentioned that. So for the current image model that you saw in those results, we did use AutoML just to try to get the tasks done in parallel. I built the text model, and my tech lead built the image model, but he used AutoML to do it. There's some issues with AutoML. I don't think it's quite ready for prime time yet. My biggest problem with it is that it only allows a maximum of 1 million images, which is really bad for us because we have tens of millions. And so we just felt it wasn't getting enough training data to be performant. The other issue with AutoML is that if it detects any duplicates at all in the images, like let's say different items were assigned to the same image, which happens all the time in e-commerce, isn't a big deal. But for some reason, Google's AutoML just freaks out, and it completely shuts down the job and restarts. And that was a huge problem for us because it was causing a lot of iteration issues. So we decided ultimately what we need to do is really build this model ourselves custom, because we get access to all the training data that way. We don't have this duplicate image item issue where the training just stops because duplicate images are detected. So that's the way we had to go forward with that. Yes?
What kind of performances are you looking at when it comes to your automation process? What bottlenecks do you see there, and what part of that is the training? What time frame do you see within your training process?
Okay, so the training actually goes quite quickly. Part of the reason for that is with TensorFlow, you can take really large data sets and you can split them into very tiny batches using the tf.dataset API, which is available in TensorFlow. It's really great when you're dealing with issues of scale. And you can also train on a machine type that you choose. In my case, I choose a V100 GPU, which is very fast. And I also use convolutional neural networks, which you can calculate in parallel. So they're very fast, unlike recurrent neural networks, which are really slow because you have to calculate them in series. And we can get the whole thing trained on 14, actually I tried it on 18 million training examples, and the whole pipeline runs in less than an hour. So it actually doesn't take very long. Now the image model, that's probably going to take a little longer, but we haven't timed that. It would probably need to take well under 24 hours in order for it to work. But we haven't done any timings on that yet, so I can't give you any feedback on how performant that is. In theory, it shouldn't take too long if we get the data in the TF records format, because then that minimizes the I/O of the reading of the image files. So the model can train a lot faster that way. And because we're freezing all of the weights in the transfer model, the only real new weights that have to be fine-tuned are those two dense layers. So in theory, it should train really fast. Yes?
Can automation through Airflow take care of like feature engineering and like optimization of parameters or hyperparameters? Like in future, maybe after a couple of weeks, the features that we are using currently become like insignificant, then can Airflow, like the automated schedule, take care of it by somewhere?
I guess in theory it could. I didn't design it that way. But one thing you can do that's really useful with this pipeline that allows you to test things really fast is, let's say that you wanted to test different hyperparameters in the model. So as part of the configuration of the entire Airflow job, you can specify those beforehand. Then you can just run the whole Airflow pipeline from start to finish, and it will do the model, and you can do the scoring and check it. And then you can do the same thing, do slightly different parameters, run the entire Airflow job again on demand, and check it again. And so there are better ways to do this. Like one thing you can do is with AI Platform, you can specify a bunch of hyperparameters that you want it to search, and then it will automatically run those in parallel as long as you configure the training job correctly. So that would be a better way to do it, in my opinion.
Yes. One more question I had was like more from a company level. How would you say Honey's shopping app would be like different from Google Shopping? Because Google Shopping already provides like Walmart, Costco, Target products on their website.
They provide targets of what?
No, they provide like a website where local stores can sell their products on, like Costco, Walmart, or Target. So how would you say like Honey is differentiated from Google Shopping?
Well, Google Shopping has a bit of a crude, it's not an app, so to speak, really. I mean, it's more like a searching mechanism, from my understanding. What we do is we have a lot of personalization and search that goes into the shopping experience across stores. So we have information about what all our users are doing, so we can surface the most popular products across those stores, which is something I don't think Google really does in the way they do their shopping experience. They also don't have automated checkout. So like if you go to Google, I think it just redirects you to the vendor's page, right?
No, they have a Google Express, which is like an e-commerce website where you can search products and it takes you until the checkout. You can pay through your credit card on their website itself.
But you have to go to their website to do the checkout, right?
No, you don't.
No? Okay, well, we can talk about that more offline. All right. Yes?
Question about how you guys handle the synonyms and like marketing euphemisms that people put in text descriptions, any text rules, and trying to decipher the decision about what you guys have.
Well, the regex rules, as I said, we're very, very early on in that, so I don't think I've fully figured that out. The text model is smart enough it should be able to do that, because the scale of data it's dealing with is enormous. So it can figure out what synonyms are based on how often they're co-located with each other in titles that match the same category label. So in that case, I think it would be okay. But the regex rules are more just meant to be like another voting member to give more confidence to the uncertainties in the system. Because if the title's really great, but the image is terrible, which can happen, then have a third member come in and kind of save the day is really nice. Yes?
Hi, thank you so much for the amazing talk. I had one question regarding the text parsing method between the text model and the regex model.
Uh-huh.
So is it the only difference between those two models, or is there a difference in the algorithm as well?
Well, for regex is very basic. So essentially all it's doing is, if you're familiar with regular expressions, it's just saying, is this item found in the title, yes or no? If it is, then we label it this. It's a very, very crude, I mean, I don't know if model is even the right way to describe it, but it is a model in a sense. It's just rules, right? Whereas in the case of the text model, that's learning what all the words represent. So like, how do you compare a vector of a title to another title, and how are those similar in an embedding space? That's a big difference between the way the two models work, right?
Thank you.
The question is, did you augment the images by making image orientations or changing the resolution of images?
No, that might be something we do in the future, but that's usually something you want to do when you have a lack of training data, when you don't have enough. We've got quite a bit. So we kind of have the opposite problem, where we're just trying to process as many images as fast as we can and just dump them all into the model at once. If we're still not getting the performance we want, we might do some of those augmentation techniques like rotation, translation, different color schemes to change the pixel values, that sort of thing, filters of color, et cetera, to try to get some more variance in the training examples that are available.
In the interest of time, we'll take one last question.
Hey, great. I actually have two questions for you. So one of them is, did you try to use some supervised learning techniques? For example, trying to do first like clustering to see all the products or text that you had would fit into that categories naturally?
No, I haven't done that because I'm trusting that the model will figure that out for me, so I don't have to. In theory, if you have large enough training data that is of sufficient quality with enough weights in the neural network, the network should be able to approximate that function itself. It would be very difficult to do that for 3,000 different categories. That would be a very difficult and time-consuming process, I feel. So we feel like this is the fastest way to try to automate it and get it performant.
And the second question I had was, what statistical technique did you use to identify this is going to be my statistical significant sample that I want to send, to crowdsourcing, and you have these results that are not either black or white?
So basically, we're just following the example that Walmart has in their paper. So they just take like a confidence level of, say, 95% with a confidence interval of about 2%, which is typically used when you're doing survey sampling. So we just take that number. So if we have 100,000 products that come in, using those statistical parameters, it's about 2,500 products. And then we look at also trying to distribute them among the categories predicted so that they're representative. So let's say we have 50 items that were in clothes, shoes, and jewelry. We try to make sure a similar proportional representative is also in that 2,500 sample. So we try to make it as representative as we can. Right, that's correct.
Thanks a lot. It was a great presentation. Thanks a lot, Jesse.
You're very welcome. Thank you.